Hello, welcome to today's video where we are introducing something known as a method of differences. And you might be wondering what on earth we're talking about. Well, we're taking a trip back to the topic of series, which is something you've probably already come across before entering into this particular topic. For instance, you might have come across calculating the series for things such as r squared or r cubed, which of course had particular formulas that we could then use to then calculate the series for ultimately any polynomial, like the series we've got on the right hand side currently. You may even have taken a look at calculating series for particular sequences, such as an arithmetic sequence or a geometric sequence. Not to worry if you haven't, but the point I'm trying to make is, although we've calculated series of various things so far, they've always been attached to very particular types of sequences, very particular types of nth terms. So what happens if it's not any of these particular types? Well, ultimately series is a very large field within the world of mathematics because you can put whatever algebra you like next to the sigma notation, and that would result in a different style of series that needs its own particular way of calculating. And yet, that's what makes the method we're looking at today so cool, because it's a method that can be applied to things that still are following a particular structure, but one that isn't quite as rigid as the ones we're looking at so far, where if the nth term wasn't exactly of the type that we're looking at, we could not work it out. And therefore I'm going to launch into our first example because it's easier to show how this stuff works and explain what's going on by looking at it in action. However, one thing I would like to point out before we begin is that there is a big clue in the name of this method. It's called the method of differences, and the word difference is basically associated with this idea of subtracting. So therefore, this method is generally applied to nth terms of sequences that have got a minus sign somewhere in them. So let's get started. We can note that r is in radians, but also the series we're dealing with involves trig functions, which straight away makes this already a lot more cool than anything we've done before with series, because we had only been dealing with things like polynomials or, as I said, very set structures if you've done arithmetic sequences or geometric sequences. Arguably, that might initially make this series look a bit scary to calculate, but therefore I'm going to ultimately give you the same bit of advice that I've given at other times when calculating series, which is that when you're calculating an unfamiliar series, it's always a good idea to start by just trying to work out what some of the terms in that series are, because you might see a pattern that might then make it a bit more clear what approach you might want to take to calculate it. So I'm going to start by plugging in r equals 1. And if we do that for this particular series, we'll get cos of 2 times by 1, in other words, cos of 2 radians, which is a bit of a bizarre number, but there you go. Take away cos of 2 lots of 1 minus 1, which is 0. And then we could continue on. We could calculate the second term, which would end up getting us cos of 4, and then cos of 2 being subtracted. We could work out the third term, and when we do, we start to see a pattern emerging. Because what you'll notice, pun not intended due to the trig function we've got involved, we've got this situation where we've got a term appearing earlier on in the series, and then that same term being subtracted later on. For instance, in the first term we had a part of it being cos of 2 radians, and then later in the second term we're subtracting cos of 2 radians, which means that cos of 2 radians part is going to cancel out. And then it happens again, the line below, we've got cos of 4 radians, and then it's being cancelled out below by minus cos of 4 radians. This pattern would continue. If you were to do the fourth term, there would be a minus cos of 6 radians that would also cancel out with the cos of 6 that we already had from the third term. But just at least calculating the first 3 terms is a good idea. What I'd next recommend doing is calculating the last 2 terms of the sequence. So r equals n minus 1, which would lead to cos of 2 lots of n minus 1 minus cos of 2 lots of n minus 2, and then also for r equals n, as that's the last term in our sequence. So cos of 2n minus cos of 2 lots of n minus 1. Because we'd already identified the pattern above using the earlier terms in the sequence, we can already deduce which terms in the sequence are going to stay behind. We can already see it's always going to be this sort of diagonal pattern when it comes to the cancelling out. So therefore, although we haven't written, as I said, the fourth term, the fifth term, and also we haven't written the n minus 2th term, etc., we already know the cos of 6 radians is going to cancel out with something later in the sequence, and we can already see the minus cos of 2 lots of n minus 2 is going to cancel out with something in the term above, even if we haven't written that term either. However, the point is, no matter how far down we go, we're still going to be left with this minus cos of 0 radians that we had at the beginning of the series, and then also we're going to have that first part of the last term, whichever term we stop at, that's going to also be left over with, because you'd need the next term afterwards to be able to cancel it out, but if we're stopping at this term, that thing is just going to be left there. This is pretty neat because it means that we can now say what this series comes to. It's going to leave us with a cos of 2n, and then we're also going to have the minus cos of 0 radians. And it gets even nicer because cos of 0 radians is just 1, so therefore, funny enough, this entire series could just be summed up using the formula, pun intended, of cos of 2n minus 1. And there you go, we calculate the series. And this is the idea of method of differences, is this situation where you're going to have a part of one term being cancelled out by that same part of the term being subtracted in a later part of the series. And you just have to be watching out for when that cancelling out is going to take effect. But beyond that central theme of parts of one term being cancelled out by that same part being subtracted in a later part of the series, the nth terms of the sequences we're doing the series for can be a lot more varied, because as long as they've got the subtraction that creates this cancelling out, then what we have can be completely up to us. But therefore, the nth terms of the sequences can be a bit more disguised. We could, for instance, have as a classic style of question a series that looks like this. Because ultimately, if we've got a fraction like this, with the bottom being factorized, that should give us a big clue that we should be doing partial fractions, because why else would the bottom of the fraction be left in that factorized format? So in fact, that's going to be the first part of doing this question. If they're very kind, they might leave that as a separate part to the question initially to give you the hint that you need to do it. But if not, still, as I said, I've identified why I'm choosing to do it anyway. But as I'm assuming partial fractions is an idea that you're already very familiar with, I'm going to fly through that process. We therefore end up with our partial fractions being 5 over r plus 3, take away 5 over r plus 4. And therefore calculating this series is going to boil down to, instead of just calculating everything as that one big fraction we had initially, we're going to be looking at it as the breakdown of these two partial fractions. Because as you'll notice, doing so has introduced this subtraction process that we wanted. But we still need to plug numbers in to see exactly how that effect will result in things being cancelled. For the purposes of exams, I would say, or at least for the exams that I teach for, it's a good idea to plug in at least r equals 1, r equals 2 and r equals 3, and as you saw before as a bare minimum, r equals n minus 1 and r equals n. That's enough to show some of the cancelling. There might be some later questions for method of differences that we'll look at in a future video where you might want to show more than that even, but this is a good bare minimum to make sure you're picking up those method marks. So plugging in r equals 1, we get 5 over 1 plus 3, which is 4. Take away 5 over 5. I'm going to leave it as 5 over 5 because then the next term immediately we're going to get a 5 over 5 anyway. Minus a 5 over 6. A 5 over 6 minus a 5 over 7. And you can start to see ultimately what pattern is going on here. Later on we'll end up with a 5 over n plus 2 and a minus 5 over n plus 3, and then a 5 over n plus 3 and a minus 5 over n plus 4. This is great news because again the cancelling out's happening, and again it's happening in a sort of diagonal pattern if you set out your work like I've done here. If you look at other resources online or in written material, you might see that people set out the work for this stuff in one long horizontal line, which is perfectly legitimate, but I find this sort of vertical layout makes it easier to spot what's cancelling out because it often results in this sort of diagonal pattern for the cancelling out. Albeit this time it's the different diagonal direction to the one we had last time. So again, the 505 is cancelling out with the minus 505, the minus 5/6 is cancelling out with the other 5/6, and that pattern will continue down. And therefore it means that the minus 5/7 would cancel out with the next term, and the 5 over n plus 2 would also cancel out even though we haven't shown it, because it's cancelling out with something from the term above. And therefore the only things we're going to be left with at the end are going to be the 5 over 4 and the minus 5 over n plus 4. And therefore we calculate the series. The only thing I'd point out is that sometimes they want you to give the answer as one big fraction at the end, which again freaks out some people because they get to the stage of the working we're at and they go, oh my goodness, we've got two fractions, why does it look different in their answer? And it's just a case of combining the two parts of your answer. So therefore creating one common denominator, it would of course be 4 over n plus 4, and therefore we'd end up with 5 lots of n plus 4 on the top, minus 20, which could then be simplified to get a final answer of 5n over 4 lots of n plus 4. And there you go, we have calculated this series too. That is the method of differences. There is more to talk about though, but we'll save that for a future video because the pattern in which the cancelling takes place won't always be with the term immediately after it in quite the same nice diagonal pattern that we've seen so far. But I'll see you in a future video. Goodbye!